Hi, my name is Ethan Nowaski, and this is the Week 3 explainer video for question 73. The question asks, prove that the expression for x of t in equation 15.55 is a solution to the equation of motion for a damped oscillator, equation 15.54, if and only if the angular frequency omega is given by the expression in equation 15.56. So first let's look at our equations that they're asking us to look at. In equation 15.54, we have d2x over dt squared plus b over m dx dt plus k over m x is equal to 0. This equation gives us the motion of a damped oscillator. In equation 15.55, we have x of t is equal to a e to the negative bt over divided by tm, or 2m, times cosine omega t plus phi initial. And this is also a motion of a damped oscillator, just in a different form. So these two equations are what they're asking us to relate each other to, and it's going to be our job in this problem to find how they're related. And it's going to be through this equation, equation 15.56, omega is equal to the square root of k over m minus b squared over 4m squared, or this is equal to omega's initial squared minus b squared over 4m squared, that we're going to find this. So the first thing we're going to want to do is we're going to want to take our equation from 15.55, and we're going to have to set it here, and then we're going to have to take the derivative and the second derivative of it. So this is going to be a mathematical proof, so you want to be very careful with your variables and make sure that you don't mix any of them up, because that could skew the final result of the problem. So I put our first derivative in as simplified of a form as I could, right here. And then I took the derivative of it again to get the second derivative, and I tried to scoop all of the values to make it so that we can see how they're going to cancel out later on when we combine them together, and hopefully that it will end up looking nice. So when we plug them all in to our equation, we plug them all in to our equation 15.54, that's our second derivative, our first derivative, and then our original one. So we're going to plug those all in, and it's going to look like this. It's going to be really long. We have our second derivative, our b over m times our first derivative, and then we have plus our k over m times our original x equation. So if we multiply, if we just do a little mental math and we put our b over m into here, we look then we see omega ab over m, and we see omega ab, factor out that e over m. So we can actually cancel out these signs right here, which will be very helpful when we look at the equation a little bit more, and we see that we can factor out this cosine omega t plus phi initial. So when we do that, we cancel out our signs, and then we factor out our cosine. We're going to actually be left with this right here, which is negative b squared over 4m squared minus omega squared plus k over m times cosine omega t plus phi initial is equal to 0. So when we have this right here, they're multiplied towards each other. One of them or both of them has to equal 0. So we have this represented here with negative b squared minus omega squared, a negative b squared over 4m squared minus omega squared plus k over m is equal to 0, or cosine of omega t plus phi initial is equal to 0. So let's solve this out first, and we see negative b squared over 4m squared plus k over m is equal to omega squared, right? And then we take the square root of both sides, and we find that square root of k over m minus b squared over 4m squared is equal to omega. And this looks exactly like this equation 15.56 that they asked us to try to solve for earlier in the equation. So we see that when omega is equal to this, k over m minus b squared over 4m squared, we can plug it in here and it will equal 0. So then when this equals 0, 0 times that will equal to 0. And that'll be our final, that will conclude our solution of this mathematical problem. Thank you.